Hi folks, welcome to the course. Today we will be diving deeper into our algorithm world. More precisely, it's about modeling these algorithms and then evaluating them to see how well they do. And that's a good step to do after we've finished with understanding what data looks like and how we can work with it. So in the story of this overall course, with the foundation set and the initiation having covered the importance of data, we can now get into our modeling. And once those models are done and evaluated, next steps are the deployment, countering concept drift, and then we can finally move into the level of AI within systems, within value chains. Before we do that, however, let me shortly repeat a few main points I had in the previous lecture. The first one being, our idea always needs to be rooted in real life. So whatever we try to solve with AI needs to have an objective and a clearly measurable success criteria in the real world, which we define as our business problem. And then once that is understood well, we will translate this into a machine learning problem that can then be approached by this algorithm, where we have to prepare the data, right? That's what we covered. But then to finally model our supervised learning problem either into a classification task or into a regression task. And today we'll also get deeper into this. How do we evaluate these different types of problems? What set of methods do you have available to do the modeling according to either a classification problem or a regression problem? Now, looking at it from the view of the entire AI lifecycle, we did cover the foundations last time, so the entire model initiation step, understanding the data set, its characteristics, preparing it so it's digestible for the algorithm. So luckily all of that is done, which means that right now we can concentrate today on the performance estimation. And for the performance estimation, there are a bunch of choices that you can do. You can see them over here. So you have to think about things like parameter optimization, about the search space and the search algorithm, and especially also about the data splitting methods. Now, all of these terms won't tell you anything because I haven't really introduced them yet. We will come to that in a second. But you should get an overview on what we want to deal with. And in this performance estimation step, two techniques are important. The one is the training of the model, where you have different things at hand. For example, again, sampling methods, but on the other hand, also the choice of algorithms and their parameters. And then in the model testing, especially choosing a meaningful performance metric and then evaluating the model so that you get an understanding for its real world applicability, its real world performance, and nothing that is too close to the original data that you might use. Okay, so let's have a look at today's objectives. First of all, I want you to explore deeper the basic concepts of supervised machine learning algorithms. And there are a bunch of algorithms out there, and there's no way to cover them all, right? There are distinct lectures on machine learning algorithms. I mean, there are even distinct lectures on supervised learning in its entirety or unsupervised learning. So we will be a little bit superficial here and just dip into the possibilities here and there, because this is no machine learning course. But still, I want you to discover those basic concepts. Second, I want you to understand the performance metrics and why it really matters which one you choose here, and especially when it comes to the difference between classification and regression problems, what suitable options you have there. Third, I want you to learn how to find the optimal parameters for an algorithm without overfitting the model. We'll get into that in a second, but overfitting means that you learn basically the data by heart, and that's nothing that we want, because then our model will not work well in the real world. And then finally, I want you to be able to distinguish between different sampling methods. Now, we did cover sampling already last week. Now, the goal is a different one. right? Before it was about selecting a relevant subset. Now it's mostly about countering imbalance, but we'll get to that in a second as well. Okay, so this determines our remaining agenda for today. First, we want to have a look at the algorithm options that you have to get an understanding for their basic functionality and for the parameters that we can use to tune them. And then I want to talk about the performance metrics and finally about the evaluation options that you do have at hand. So let's dive right into the algorithms over here. And the first question you might ask is, again, what do we need these algorithms for? Where are we coming from? If you're successful in the previous step and you collected the data that you need and you did all of these different small tuning steps that we discussed last week, then you have a certain data set available to you that you can now use to both build and evaluate your model. And it's important to note that as you only have this data set at hand, that's all that you got, which means that you need it for both, for DTR, for training your model, but also for DTE, for testing your model. So you typically split your data set. There are different ways on how you can do that, and we'll cover them by the end of this lecture. But first of all, understand that the data that you have available is not only available to your training, but you have to cut this. Because, of course, in the real world, there will be future data the model will be applied for to. Data that you haven't seen yet, because your model isn't in production yet. But still, your future model will work on this data and will make predictions on that data. So you try to simulate that by cutting out this test set over here. But what we want to talk about now is this training set over here. And what we do now, also to be precise in terminology, we will pick an algorithm and we will apply this algorithm to this training set. And then exactly what I told you last week will happen, right? If you remember this matrix of features, columns, and observations, instances, or rows. Now, the supervised machine learning algorithm will try to identify patterns in the data by mapping, again, the input, the features, to the output, the target that we selected. And as we apply this algorithm that we chose to the specific data set, to DTR, the training data set, the result of that will be a model that can now make its own predictions, right? So it's important to distinguish between the algorithm, right, the fundamental methodology, the precise steps that your computer will go through, and by that it will build up knowledge and it will build a model that is tailored to the training data, right? The model is always specific to data, whereas the algorithm is the general rule book, you could say, right? The general guideline on how your computer will learn patterns in the data, right? So distinguish between algorithm and model. And if we look at algorithms, there's a vast availability here. So if you look into the different supervised machine learning algorithm groups, you can see many, many examples. And by no way is that a complete overview. And this literally changes every day because new architectures appear every day. So as we cannot cover all of them, I'll try to give you at least one example per group. So what we will work on is I want to give you examples for regressions, for decision trees, for Bayesian methods, for kernel-based methods, for artificial neural networks. Also a little bit, we look a little bit into ensembles, but they will be more important as we progress in this course. And for now, I will skip association rules and instance-based methods. So let's dive right into the first example here, which is the regression. And the linear regression is a great candidate to start with. It's one of the most basic forms on how we can learn patterns within data. It's something that you are probably already familiar with. It's typically taught in statistics 101 classes. And the idea here is that you have four distinct properties of the linear regression. Observations, or a single observation in this case, an output value. By the way, observation would be called a feature in our logic, and the output value would be a target, or in statistical terms speaking, the output value would be the dependent variable, whereas the observation variable is the independent variable. You see that there are a few terms on how to call things, but now I think we're clear on that. You have the gradient and you have the interception. And a linear regression represents a statistical procedure that explains this observed dependent variable, the y, by one or typical more multiple independent variables x, and then it maps the underlying relationship in a so-called regression graph, right? You can visualize this very nicely on the one hand by a formula, but also on the other hand visually as a graph shows over here. And now if you add new data points, this obviously influences the calculation of this linear regression line, right? Things can change, the gradient can change, the interception can change, and again, this can be depicted as this equation over here with y equals a plus x times b, and again there can be multiple x's over here. Again, very nice, easy to understand, easy to visualize, very transparent also, by the way. You can simply plot it in the two-dimensional space at least, and have an understanding on the relationship that you would try to cover here, right? So quite a nice tool to start with. Then you can vary the regression to come up with a logistic regression, and a logistic regression is a statistical method for modeling the probability of a binary outcome, 0 or 1, again based on one or more features or independent variables. And unlike the linear regression, this relationship that is being mapped now uses an S-shaped curve instead of a linear relationship. And it is often used for classification problems, right? The one that I showed you earlier, the linear regression, is, as you can hear from the name, a regression predicting a numeric variable. Now, it gets confusing because the logistic regression is used for classification problems, right? So it provides the odds ratio for the likelihood of an event occurring in response to these independent variables, to the features that you have at hand, right? And then you get this P of y formula with 1 over the base of the natural algorithm. And if you plot that, you can see it looks like this. If we take the example that we had earlier of the students, right, you will get this distinguishment between the two classes, class passed and not passed, which is in our case the dependent variable, mapped to the independent variable of ours studied, as you can see over here, right? So again, confusing because logistic regression is used for classification and not for regression, whereas a linear regression is. Now let's move over to the next class of algorithms, the decision trees. Now the decision trees have 3 important properties. They have root nodes, decision nodes, and leaves. And a decision tree is a great thing, also in terms of transparency and understandability. And again, don't underestimate this. You're trying to solve business problems, and these business problems are areas where domain experts have worked on a lot. And if you can transport the fundamental workings of your algorithm to these domain experts, you can only win in that case. Especially if you're working with engineers, for them it's very important to have an understanding on how the algorithms works. So again, coming back to the decision tree, that's what's so great about it, because it represents a decision procedure based on a sequence of questions that are being asked, and each of these questions is called a test. And then the answer to this test is represented by making a decision in this decision node in the decision tree. And then depending on the answer to that question, to that decision node, it will be determined which question will be asked next. And questions will be asked until a decision is reached. So the decision is then the final prediction of the decision tree. And I think this makes it very clear, right? You start from the root with one question, and depending on the answer, you will get into a different node and into a different node, and the final answer that you will be provided with is then the leaf. And that's a very basic form of a decision tree. It does not necessarily work well on real-world data, but there are variations of the decision tree, more complex structures like a random forest, for example, which is both a decision tree and an ensemble, which builds, you can tell it from the name, entire forests of these trees in a randomized way. And by combining these, typically also gets very good outcomes. But for now, it's only important to understand the fundamental workings. And I think that's very nice because it's easily explainable to people who are not from the field necessarily, although it is heavily limited in what it can do. But speaking of being limited, let's move over to the next set of algorithm, the Bayes ones. And Bayes classifiers are very powerful tools and come from the field of statistics, something that you would also typically learn in your early mathematics statistics classes. Again, like in the previous ones, we have observations and outputs, so in our machine learning logic, features and targets. And now a Bayes classifier is a probabilistic model, and that differentiates it from what we saw earlier, right? Now we're doing our classifications based on the Bayes theorem, so on probabilities. So this model applies this Bayes theorem to classify data points, now based on the likelihood of features belonging to certain classes, right? You can see this over here in the formula, the probability of y given x. And in its vanilla form, it assumes independence between features. So this is commonly known for working really well for certain tasks like spam detection and text classification. That's where it's been widely used in the 90s and early 2000s. Nowadays, most of these tasks are performed by artificial neural networks, but nonetheless. So I already said that there's the case of assuming independence between features. This specific case is called naive Bayes, right? So it assumes conditional independence, which means that every feature that you have in your data set X is statistically independent, and every feature contributes also independently to the probability of its target of this class Y. Now that's a pretty let's say unrealistic assumption in the real world. But what's interesting is that despite this simplicity and this unrealistic independence assumption, it does perform surprisingly well. Although I have to say again, like over time, it became less important. And now there are ways on how you can tune it. I should maybe repeat this and be clear about it. All of these algorithms that are being shown here have options to tweak them, to influence their behavior. And these options that you have are called parameters. And of course, you don't know which parameters are the best ones for the case that you have at hand. It's something that you have to try out, and we'll figure that out in a second. But one of those parameters for naive Bayes is setting the distribution of values for each of these features. So what distribution do you assume? Is it, for example, Gaussian or multinomial? And by that you can tune your model. But we'll get to that in a second. Just for the moment, it's important for you to be aware of the fact that we have these parameters that can influence the behavior of our algorithm. Now, let's move over to a different kind of algorithm class. More specifically, a support vector machine, which sounds interesting, right? A support vector machine does sound very fancy, but it's actually not that hard to explain. So support vector machines are based on the concept of a so-called hyperplane. And you can see a nice example over here, which is two-dimensional, which is something that we can nicely visualize. And if we have these two dimensions, a hyperplane is a line which separates the instances into two separate subsets, right? So binary classification in this case over here, pink points and blue points. And those instances that are closest to this hyperplane are called the support vector. So they support the way that the pattern is being recognized. They support the way in distinguishing between those classes. And now the aim of a support vector machine algorithm is always to maximize the distances to these support vectors. So to be as good as possible in distinguishing the classes that I'm interested in. And the interesting thing about support vector machines is they can be used for both classification and regression problems. Again, in its vanilla form, it cannot work well with, or it doesn't work at all with multi-class problems, but there are easy fixes to that. So for example, you can do 1 versus 1 classification if you have multiple classes at hand, or you can do 1 versus all classifications. And the nice thing is this is nothing that you have to implement yourself. In the common Python packages that we use nowadays, you simply select whether this is a multi-class problem or not, and in the background it will perform these 1 versus 1 classifications or 1 versus all classifications and calculate you all the scores. So that's very neat. So we have this idea of support vectors and hyperplanes which can separate the data. Now, the example that I brought with me over here is a linear one, as you can see, right? So there's a linear relationship assumed, and we divide these two classes in a linear manner. However, it's important for me to note that that doesn't always need to be the case. So also nonlinear relationships can be addressed by using so-called different kernels. And kernel, again, is a parameter that we can pick for the algorithm of a support vector machine, right? And there are different ways, as you can see, right? We can have polynomial kernels like the one on the left over here, right? In this case, even with multiple hyperplanes. You can even have radial kernels, right, with these round separation boundaries over here. Again, coming back to the initiation step, that's why it's so important to have a look at your data distribution, and also visualize it if possible in the two-dimensional space, like over here, because then you can get a feeling for the underlying relationship of the patterns that you want to find in your data, and then hopefully pick the right algorithm, because that's what it's all going to be about, right? We will go through these algorithms, and the idea is pick the best one for your problem at hand. And other parameters that are typical for SVMs are two. The C is the number of falsely assigned instances. So how many of those will you tolerate, because your model will make errors. For example, you can see a few over here in this polynomial example. And epsilon, which defines the range of acceptable error. So that's this range over here. And of course, that the output of your model highly depends on your tolerance in both of these numbers. And finding the right one is not too easy, and is something that you typically have to play around with when you optimize these parameters by trying out different combinations. Okay, now let's move to a class that is one of the most popular ones right now, the so-called artificial neural networks. And they're a very interesting case because they're inspired by us humans, basically. So they're based on the idea of biological neural networks, which is our brains, or not only ours, but also those of animals, of any biological being. And what researchers did in the past, they tried to mimic or recreate the way that our brain works by having this artificial neural network. And they were quite successful in it, although with the rise of more computing power, these became more and more capable, because the more computer power they have and the more data they have, the better they work. And in some cases, they are comparable, if not even better, than human outcomes. So I had a very interesting story when I was working with IBM, and I did my PhD there. I went over to the lab in Böblingen, the research and development lab, and I kind of flexed with the cool stuff that I'm doing, like identifying needs in social media with artificial neural networks. And they were like these old engineers, right, who've been working on machine learning for decades. And they're like, Yeah, we basically did that in the early 90s. So that's true. They used in the very early 90s, they already used artificial neural networks to detect fraud on signatures of credit cards. Um, well, the only difference, and it is the same fundamental working as the one that I'm gonna be showing you in a second. But what's interesting is that the models were way smaller and they took way more time to calculate. Nowadays, you can calculate this with a simple smartphone in a matter of seconds. It just took them so long. So the computational capabilities that we have today, they really give rise to, on the other hand, capabilities of artificial neural networks. But I'm getting ahead of myself. What are artificial neural networks? Well, one word that you can see here already is the word of neurons, and they are the fundamental building block of a neural network. Every neuron has an input, an activation function, and then an output function that allow it to process and transmit information. So something goes in, by a function, this single neuron is activated or not activated, and then outputs something. And these are organized in so-called layers. So the input layer acts as a gateway, receiving the data that we saw earlier, the raw data, and passing it on to the network. Passing it on precisely to the middle layers, also called hidden layers oftentimes, which then transform this raw data by applying potentially different activation functions that try to extract the significant patterns and features and to understand that and process it. And you typically have multiple of those middle layers or hidden layers. That's also where the term deep learning comes in, by the way. So typically a neural network is called a deep neural network once there are 3 or more hidden layers or middle layers. And as of now, like the majority of ANNs that are being utilized are deep learning networks. And then finally, you have the output layer that synthesizes everything the network has learned and provides a refined and calculated response. So the answer again, the target that we want to predict based on the input. So it looks something like this, right? You have the input layer with our features x0, x1, x2. And then all of these neurons in the input layer are connected to the neurons of the next layer, the middle layers, which you can see by these weights over here. And you can see that it gets very complex very soon. So typically you do not have just one middle layer with 2 neurons and 3 neurons in the input layer, and then finally one output layer, which gives you the prediction of our target Y, but way more, right? Like 100 or 1,000 neurons per layer, and then multiple layers between I don't know, 3 and 100, depending on the architecture that you pick, and then it gets very complex. And that's also why neural networks are by no means transparent to any user. There are ways on how you can deal with that later, but we call this the black box characteristic of artificial neural networks, because it's impossible to understand how it will come up with its final prediction. Again, in theory, you could look at all of these different connections between each neuron, but this will get too complicated. But let me give you an example. Let's go through an example how an artificial neural network works. And we want to do this with a typical network with a typical example from the field. So neural networks work typically very well with unstructured data. So in our case, let's pick very unstructured data, images. And we make it even more unstructured because we take handwritten numbers. So you can see a bunch of handwritten numbers over here. By the way, this is called the MNIST dataset, which is a very common dataset to do your first machine learning steps on. And that's also something we will utilize as part of this course's exercise. So how can an artificial neural network recognize a handwritten number? Let's take one of these numbers from the dataset that you can see over here. In this case, a 9. And now what we do is, you can see it by the resolution over here. This 9 consists of 28 by 28 pixels, so 784 in total. And as this is only black and white, we have different shades of gray. So the way that you transform this now for this artificial neural network is every single pixel, so say 784 in total, will be one of the input variables here. So will be one neuron in the input layer. And now each of these have a value, a gray value to be precise, between 0 and 255. If you look into how coloring works in computers, you have these values for each of the pixels, which determines their color. In this case, it's rather easy because it's only one value, because it's only black and white and only gray for this case. So we go into with that number. So the input layer receives a gray value between 0 and 255 for each individual pixel of the image. And now what happens next is that this information is now passed on, so these different gray values, into all of these middle layers that are connected. So after the input layer, the data passes through one or more, in our case now 3 of these hidden layers. And each hidden layer consists of neurons that apply, in this case, a weighted sum to the inputs and pass the result through a typically nonlinear activation function. And this is again a parameter that you can choose for yourself. So what is this activation function for these neurons? It could be something like sigmoid, hyperbolic tangent, ReLU, so rectified linear unit. There are many ways. We look into the Python packages to give you an understanding. But again, you have to pick an activation function for each of these neurons, and you do not necessarily know which is the best one for your problem at hand. Again, that's a parameter that you will have to play around with. And then these hidden layers enable the network to learn the complex patterns of the data by combining the inputs in a nonlinear way. And basically that's like where the magic happens, right? It's really interesting to see that it works, but explaining in detail why it works so good is sometimes really tough. We can just say that ANNs are good at covering these nonlinear relationships, and in reality most of these relationships are nonlinear. So applying a linear regression is great in theory, but doesn't work in any real data set. And by having these nonlinear activation functions in the neurons, you typically allow this to work way better than any linear classifier. Now, what it tries to do here, of course, is to predict the outcome. So the handwritten digits are between 0 and 9, so there are 10 possibilities in total. And one of the assumptions that we have, and that has already been shown in research, is that abstract features in our case now these images, such as the edges or the circles, are recognized in the intermediate layer, while other shapes are derived in the following layers. That's, by the way, a great property of artificial neural networks, because it means you can take a certain part of them, we call that freezing the layers, and then moving it to a similar but different problem, and it will keep its knowledge, for example, on circles and edges, or if we work with visual data, more general on, for example, what planes look like, what cars look like, and we can still so-called fine-tune that then later by having these abstract features learned in the early stages and then the more precise ones in the later ones. But for now, that's not important for us. What's important now is that we finally have also the connection, of course, of all of these middle layers to the output layer. And the final layer is now this output layer, and it typically has, I think always, as many neurons as there are classes. So in our case, we have these 10 classes for the digits 0 through 9. And now, again, you have to pick an activation function here, and for classification, this is typically the softmax activation function, which is used to provide a probability distribution over those classes for the output over here. Again, you can pick different ones, and then probabilities are assigned to each of those classes, and then it will finally come up with a solution to that. And that's how neural networks work, only that this is rather a simple version of one. There are over thousands of architectures on how we can design that. And I just want to give you 2 more examples of artificial neural networks so that you have heard about them. As we continue in this course, I will give you more examples when they make sense for the task at hand. But for now, you should at least have heard about this type of neural network called convolutional neural networks. And that is a special type of artificial neural network where you have, again, multiple hidden layers, but they have special purposes. So now those layers have serve different functionalities. You have so-called convolutional layers. They reduce the number of required parameters by convoluting the input data. You can see it over here, by the way. That's a nice depiction on what happens with an input picture in a CNN. You have these pooling layers, which have the aim to reduce unimportant information by pooling multiple information and then only passing on the strongest signal. And you have fully connected layers. By the way, a few of those examples you've seen earlier where we fully connected the hidden layers. So this is similar to those of the standard artificial neural network. And what's really interesting is that these CNNs work incredibly well with visual data, especially in high dimensionality of pictures and videos, which is really, really interesting. And again, you can tune those. So for CNNs, again, you can distinguish between the order of the layers. So over here we have, for example, convolution and reload layer, then we pool again, then we convolute again, then we pool again. But you can combine these architectures in any way you want. Hopefully it will lead to better results then. And of course also the size of these, of the amount of layers, of the type of layers, but also how you combine them plays a large role. And in some stage, it might not give you any meaningful results, but it's something you can play around. A different class of artificial neural network are the so-called long short-term memory networks, or LSTM. They are a subset of so-called recurrent neural network, which we won't cover in detail here. But I want to shortly talk about them because they work really, really well with time series data. And again, they're designed a little bit differently because they also have information about a state for each cell. And this state is regulated by input gates, output gates, and forget gates. And especially this forget gate is very important because what LSTMs work really well with is typically models working with time series get stuck in, let me just show you. So if you have a relationship which looks somewhere like that, and this would be a local optima over here, traditional methods would get stuck in cases like that over here. But the great thing about LSTMs is that it has a good combination of, and that's where the name comes from, long and short-term memory, right? So it's better at finding these global optima because it will not overfit on certain minima that you have in that relationship. And the magic to that are those forgetting gates, because they make sure that the model in some stages will still move on without looking too much at those smaller portions. And this combination of a long-term capability with a short-term one makes them really powerful for time series. But we'll get to use them as we progress in the course. Now, you heard about a bunch of possible algorithms. And again, that was a very, very, very superficial overview. Now, you might question, how do I choose the right one for my task at hand? And that's a really tough answer, and I can't give you that answer. There are a bunch of rules though. So there's this nice figure from scikit-learn where you can go through is on how many samples do you have. Then it says get more samples and asks you different questions like a decision tree, and then tells you which algorithm to use. It's a little bit outdated, to be honest, but it's still helpful when you start working with machine learning in the beginning. Now, there are a few characteristics that help you determining what algorithm you should pick. The first one is a few ground rules, like the number of observations. How large is your N? Especially these traditional methods that I showed you earlier, like a decision tree, like a linear regression, they work great also with small amounts of data. And of course, they assume linearity. At least the linear regression does. But some cases, it doesn't work too bad. For artificial neural networks, you need large amounts of data, hundreds, thousands, millions, billions of data points. That's where they excel. That's where they work really, really well. So again, looking at your data is really important in the beginning. The second one is the logic. That's what I already said. Like, looking at the data, plotting it is, do you see rather linear relationships in the data, rather nonlinear ones? And this should help you also in determining which algorithm to pick. And by the way, the other logic is, of course, are you modeling a regression problem or a classification problem? Because this also limits the options that you have at hand. Third one is explainability and transparency. Again, from a scientific point of view, not that important. In reality, one of the most important characteristics, right? You have to make people understand how and why a model comes up with its predictions. Very important aspect for trustworthiness. We cover this deeper when we come to human AI collaboration and what is important there. But for now, explainability and transparency is important. And again, the more complex the models get, like artificial neural networks, the less they are explainable and transparent, but typically they perform well. On the other hand, we have cases of linear regression and decision tree, which is easily explainable, but then the performance might not be that good. And then finally, a lot of that, like which algorithm to pick for which case, is experience and intuition. If you've been a data scientist for a bunch of years, you get this natural feeling on what could work well here, and that's how you utilize it. And I hope as part of this course, as you will try out things in Python and work with multiple data sets, you will also build up a little bit of this experience and intuition in what algorithm to use. But maybe in a nutshell, there's no easy way on how to pick the right algorithm. This should help you a little bit in determining your choice. Okay, so now that we have an overview of the algorithms, let's have a look at the performance metrics that you have at hand. And again, let's remind ourselves, what do we need those for? So we have our training data set at hand. We identified an algorithm that we want to use, which resulted in a model. Now we have this model M. So the application of the algorithm led to a model which captured, hopefully, the patterns of the data in our training data set. Now at this point, we take our test data again and now apply this model to the unseen test data set. And the great thing is that for this test data set, we know the so-called ground truth. So as we cut it out from the one above, we know who of those students passed the test, for example. We know who of these people in the treatment have cancer or no cancer. So, but this model has never seen this data because you did the data split over here, right? Where you cut the test set out. And now you can apply this model to the unseen test data set. And based on that, you can calculate different performance metrics, and that allow you to evaluate how well your model works. And we'll start with classification because that's very easy to understand on how it works. As I said, for this test set, you have the ground truth. And let's work with a binary case because it's easier for the second. Of course, that works also for multi-class cases. And again, let's say you have a positive and a negative outcome. So someone passed the test, did not pass the test, the machine failed or did not fail. This person has a tumor or does not have. And now you know the ground truth from your test data, and you know the prediction from your model that you apply to it. And from these, the following metrics can be derived, which are the core metrics in classification, and not only for machine learning but across the board. So if you look at medication, for example, certain drugs that you're using will report their true positive and true negative rates when it comes to the detection of, for example, COVID in the COVID test that you can buy from the drugstore. And they have these rates as well because there's no machine learning at place, but there is a chemical process trying to predict whether you have a certain disease or not. So these are very common across different fields, not only for machine learning. And they are the true positives, so those are those that were predicted as positive and were in fact positive when compared to the ground truths. You have the true negatives, those were the ones that are predicted as being negative and were in fact negative when looking at the ground truth. And then you have the true interesting cases where of the false negatives, so that's where your model thought it was negative when it was in fact positive, and the false positives is where it predicted being positive when it was in fact negative. And based on this, all the other metrics for classification are calculated. Most important one being accuracy, very typical. So this describes the relation between the correct classifications and the total number of samples that you have. It's good to get a first insight. It has its flaws, as you'll see in a second. You have precision, which is the proportion of correctly predicted positive classes regarding all the positive classes that you have. And you have sensitivity and recall, on the other hand, which is the proportion of corrected predicted positive classes regarding all positive cases. And in reality, precision and recall are typically hard to optimize at the same time. It's easy to get high precision values, it's easy to have high recall values, but the other metric typically suffers. And that's why you need a different score. So that's why the F1 score or F1 metric is very, very common, because it's the harmonic mean between precision and recall, right? It does not only try to optimize for being as precise as possible in your prediction, even when this means ignoring a vast area of other positive classes, but it also not means simply aiming for recall, which means hitting as many as possible of the classes, even if you make errors in that. So that's why the F1 score is very common and very popular here. But for some cases, you might want to fine-tune this even more. So there's a larger, more abstract concept called the F-beta score, or F metric in general, which gives you the option to weigh whatever is more important to you. And F1 score is one instantiation of that F-beta score that you can see up there. So you ask for the question, what is the performance of the model weighting precision and recall by this factor beta? So you basically ask for the F1 score, where beta is 1. How good is the performance if we emphasize recall and precision in an equal way? If you decrease the beta now, you value precision more than recall. And if you increase beta above 1, you weigh recall more importantly than precision. And of course, you can pick any number for beta. These are, by the way, the three most common ones, F1, F0.5, and F2. But again, that's why it's so important to look at your business problem, to see what does solve your business problem in that regard. And we'll get to that in a second. But that's a very quick overview on the metrics that you have at hand for classification tasks. Now, let's look at regression. And for regression, two things are important. You also have the prediction over here and the actual ground truth. Let me shortly highlight that, right? You have the y hat, which is your prediction, and you have your y, which is the actual ground truth. And just like before, all the metrics are based on that. You have the mean absolute error that defines the average distance between every single data point, and the arithmetic mean, which has its pros and cons, but it's a good way to start with. You can weigh outliers more by using a mean squared error over here. So by having the square over here, you want to put a penalty on those cases. You can take that again and then calculate the root mean squared error. Also very, very common. You have traditional metrics like R squared, that you might be familiar with that one from your statistics class. Right, and there are like even more. Those are just for examples. And just like with precision recall, it's not the best idea to look at a single metric here, but to have multiple ones. And also, like earlier, here connect those to your initial problem that you're trying to solve. How much does an error cost me? How can I weigh this into the metric that I choose? Again, that's why it's so important. I keep repeating that. But to understand the business problem that you're trying to solve, connect it to the data that you have at hand so that it's well suited for your problem. Pick an algorithm that is able to capture that, and then also pick a evaluation metrics which will help you in answering those initial success criteria that you had from the field for your business problem, right? And this brings us to the question of how do you choose the right performance metric? Again, recall what is the underlying business problem and which metric addresses this problem precisely. You need also to consider the distribution of your data. That's why I'm always stressing that, which we'll see on the next slide. So if you recall this example that I had earlier, where we had to identify unhappy customers in the data, there we had a very, very clear message from the customer, because we know that the costs for winning new customers are at least 5 times higher than turning unsatisfied customers into satisfied ones, right? So it's more cheaper for me to make an unsatisfied customer happy than getting cold call new customers. So of course, in this case, we picked a score like the F2 score with a higher beta, because recall was more important than precision here, right? We would rather make a mistake by calling up a customer and offering them some kind of benefit when they were never unhappy in the first place than missing out on one customer who was unhappy and never received a phone call. So much for customer satisfaction prediction that we did. What about rare disease detection? What do you think is the right way there? What should we emphasize? Precision or recall? That's something that we can definitely discuss in class. But I want to stay now on the modulation initiation step, on this distribution of the data and why it matters so much. And this comes back to the imbalance. We talked about this whole genome sequencing last time. Now I want to make an easy example to show you why imbalance of data points is so important. So let's have an example over here. We want to predict if a ball is red, and of course do this with a supervised classification model, right? Pick a decision tree or logistic regression, whatever you want. And now in the case on the left, there is no class imbalance, right? We have the same amount of red and not red balls over here. And now on the other hand, we have a case where we do have a data imbalance. So now the red balls are the minority. And again, that's very, very typical to happen, right? So one case, no class imbalance, and the other case, we have highly imbalanced data set. In many use cases, if not in all use cases in the real world, you will have exactly this class imbalance that you saw on the right-hand side. So this is where it's about the detection of the minority class in the crucial task. Things like cancer detection, things like failure detection of machinery, credit card fraud detection. These are the rare cases, but those are the ones that you're interested in. That's why you start with this product in the first place, is you want to identify those rare cases, right? So the data imbalance is so typical. It's I would say the absolute standard. And why is that an issue? Because broadly speaking, the algorithms tend to ignore this minority class since they optimize for an overall measure of goodness like accuracy. And we'll see that in a second. So let's have an example over here where we have, again, a ground truth and now different predictions of a model. We'll start with the case of no class imbalance, right? So our model is entirely random, right? There's no logic behind it. It will just randomly pick 25 balls as being red, 25 as being not red. And you can see the errors resulting from that, right? In 25 cases, it is by accident correct. In other 25 cases, it's not. So we have a very evened out confusion matrix. Oh, by the way, I forgot to mention that that's what we call a confusion matrix, right? This overview of true positives, true negatives, false positives, and false negatives. And you can also calculate from that the so-called marginal frequency of the machine learning classifier, the prediction, and also the marginal frequency of the ground truth. Now, if we take our metrics that we saw earlier, accuracy and recall and potentially also specificity, you can see that for the no class imbalance, they give you a pretty good understanding on how well your machine learning classifier performs, right? If we take this calculation, you result with an accuracy, so short is called accuracy, the larger term is prediction accuracy of 50%, 50% recall, and 50% specificity. So that is interesting because it's, I think, an honest depiction of the capabilities of the model that we have at hand here. It's entirely random. Our accuracy score reflects that. Now, however, we have an imbalanced problem. and let's say we still do this by random. There's no intelligence to our classifier, but it knows the marginal frequency of the ground truth. So it knows that those red balls are very, very rare. So it will predict way more cases as being negative than they are. So this means, now remember, I'm interested in the red ones, and in the red ones it makes a 50% error over here, right? It only assigns half of those ones that I'm interested in correctly. But because accuracy doesn't account for imbalance, you can see a very nice score here, right? You will reach an accuracy of 90% with a, again, random classifier that is only, where its only knowledge is the marginal frequency of the ground truth. And also the specificity is really good, right? We can see that's in the recall that we have an issue, but that's why it's so important to pick the right metric. And if you would have chosen a F1 metric or F0.1 metric, or if you would have taken precision also into account, you would have seen that. But by focusing on a metric that is insensitive to class imbalance, like accuracy, you have huge problems. And that's something I've seen across the board in the past 10 years of my career, in practice, but also in research, is where people will report accuracy for imbalanced data. And that is a terrible idea, as you can see from this example. And of course, everyone is happy with nice results. Oh, look, I achieved 90% accuracy. But your model did not learn the pattern here, because it just ignored the minority class. And that's why it's so important to never use accuracy for imbalanced problems. Okay, we'll definitely ask that in the exam. I hope you understood that now. Okay, now let's look into the evaluation options that we had, because I did simplify a little bit, and now I want to elaborate a bit more on the steps that we have at hand here. So there are different possibilities on how we can split and evaluate a model. Right now, I simply said we'll cut out a training data set and cut out a test data set, what we see over here. But we have to be more precise now that we understood how that works. There are two questions that you need to ask yourself. First one is, do you want to optimize the parameters? These little options that you have when you chose an algorithm, right? You remember for support vector machine, it was the C, for example. For the deep neural network, it's a question of activation function, of how many neurons per layer, and so on. So do we want to optimize these parameters? Then we have to choose between a percentage split and a cross validation. If we don't want to do that, if we do want to optimize parameters while also making a good split over here, we have two options, which are either a global holdout set or a so-called nested cross validation. And you can combine three of those also again with sampling. Let me start with the most, not common, but most basic form of splitting your data. And let's ignore parameter optimization at the beginning, right? So no parameter optimization. We're happy with the parameters that we have, and we want to do a so-called percentage split. Let's have a look at the original data, and of course it's imbalanced, right? As I told you, that's the real case. Now, what you can do is, because again, this imbalance is an issue not only for your performance metric, but also for the model itself, because again, it tends to ignore the minority class. You can counter that because in training, anything is allowed, right? I can do a lot of stuff, not in testing, right? Testing always needs to be my cutout test data set with the same distribution as my original data, with the same distribution that my model will be faced with in the real world. But in training, you can do nice little things. And here comes the sampling again that we already briefly touched in the data initiation. Because what you can do now for training your data, to also counter the imbalance in having a percentage split, is you can undersample, which means you will remove instances, observations from your negative class, from your majority class. And by that, you're forcing the model to also learn the properties of my interested minority class. That's undersampling. You can also do oversampling, where you will simply duplicate instances from your positive class, from your minority class, and then have potentially a smaller share of cases from the negative ones. Or you can use something like SMOTI, which will generate synthetic new data from your minority class based on other data. This might not end up in anything that is semantically meaningful, right? It might generate weird pictures, but it might help the process. But then again, super important, the test data that you cut out in the beginning, it can never be part of the training process, and it needs to have the same distribution, right? No sampling for a test set, really important, because the test set needs to be representative of the real world that your model will work in. And don't use the same data for training and testing, right? So we have to cut this out at the beginning. And coming back to a problem I posed in the last lecture, the whole genome sequencing, we can now answer this question. Again, remember, we have DNA information, a very high P, very, very many features. And now we have the issue that the model will not learn because the positive examples are a few hundred, whereas the negative examples of this rare disease are millions of data. Again, with what we learned from last time, you would now plot this data, you would see this imbalance, and now you can counter that by, for the training, for example, oversample the positive and potentially also undersample the negative examples to now get a balanced set for training data. That sounds great. And I also said never use the same data for training and testing, and that is true. But in the real world, data is very valuable, and in many cases you do not want to throw it away. So researchers came up with an idea here as well, and that is called cross-validation. So same example as before, right? There we talked about percentage split, so taking out a test set like 20 or 30%, moving it away and using the rest for training. Now the opposite, not the opposite, but the other way that you can approach this is not percentage split, but cross-validation, which works like that. You have your original data set, again, imbalance in this case. You cut it into different smaller data sets, in this case, 10 ones. And you do this for both the positive and for the negative. And this is called a 10-fold cross-validation. Now you're building the folds with something called stratified sampling, which I introduced in the last time. What stratified sampling makes sure is that we have the same distribution over here in the original data set, also in our single subsets over here. And now what happens in 10-fold cross-validation is it will do multiple training and so-called validation runs, right? So it will train a model on your data sets A1 to A9 together with C1 to C9 and will test it. It's testing, but we rather use the term validation here. It's called cross-validation. And we validate it with one thing that we cut out from here. And now we repeat this step over and over again. That's why it's called a 10-fold cross-validation. You could also do this 5-fold or 3-fold or 20-fold, right? And then, of course, these subsets would change. But now you do this 10 times, and then you average the results. And of course, in theory, you're now using the same data set multiple times, and sometimes a data point will be part of the testing, and sometimes will be part of the training. But as you do this multiple times and you shuffle around and only take the average, this does not violate the idea of data leakage. And speaking of data leakage, what is that? So data leakage is using information in the model training process which should not be available at that stage for predicting, because what will happen here is that you will overestimate the model's power when it will be finally run in a productive environment. And it's called data leakage because the idea is that data leaks through, which should only be available in testing, into this training phase, which will then lead to our predictive scores, like accuracy of one score, to be higher than it would be in reality. And there are different things different types of data leakage, right? So there's feature leakage. So you have a proxy for the label or the label itself, right? So let's say you're interested in predicting the yearly salary, but the monthly salary is part of your feature set. Well, then your algorithm, if it's worth anything at least, will detect this heavy correlation and will then use this feature, of course, right? So that's the one type of leakage, of data leakage. And that's why it's so important to look at your data set in the first place. Next one is time leakage. if you work with time series data, it's really important that there is like a chronology in that data, and you have to make sure that you do not transform any information into the model that should be unknown there, right? If I accidentally have 2024 or 2025 in my data set, but of course in the training phase I could have never seen that, because of course I can't move into the future, then that's an issue. Or grouping leakage, so by not including a grouping split column, right? By having this implicit group information as part of my feature set. So the main message here is be very careful, because this typically happens, and it happened to me as well. It's a very typical thing to happen, but watch out for this, for these too good to be true performances. And this is especially important in pre-processing, right? If we go into Python code, so let's say you normalize, we talked about normalization, right? Moving all into the same area of range of attributes, or sanitize your entire data set, then there is data leakage, because your model knows more than it can or should know at this point, because now your model knows the full distribution of the data. So never do that. So calculate the parameters for rescaling within each fold of the cross-validation, right? And this leakage, it happens even if you don't explicitly understand it. The model will do it for you. So very important issue. Look out for data leakage. Okay, so but now we covered percentage split and cross-validation. Why we do that? Because of data leakage. Now the only thing remaining is the optimization. And the question is, how do we know which parameters to choose? Which are the best parameters for our model at hand? And I think this is a really nice depiction, because let's say we have two parameters, and we're interested in the optimum. Let's say this one over here is the optimum. Now we don't know how to combine these two features, right? Let's say the C and the epsilon of a support vector machine, right? If we do a bad combination, we might end up somewhere here or somewhere here, but we want to have this perfect combination of parameters where our model performs best. And there's no way to know that beforehand. So, well, you might have a little bit of intuition, but you have to try this out. And one of the most common ways to try this out is a so-called grid search. It's a very simple way of finding good parameters by simply brute forcing discrete values that you predetermined yourself. So what you do here is you define the possible values, or the range of values with an increment. This is called the search space, and you do that for every parameter. And now what will happen is your grid search will brute force every combination of every possible value and will be tested in this so-called grid search. You will need, as part of that, it's one line in Python code, to select a performance metric. So what's the single performance metric that you want to optimize for? Again, careful with accuracy. And then choose a test data set that will be used to validate the model. And this can be either a so-called global holder set, something that you set apart at the beginning and moved away, or you can use a nested cross-validation, which I'll get to in a second. And now all of these defined combinations are tested during the grid search, so different C's, different epsilons, and then the result is the value for every parameter which was part of the combination with the highest performance. So you might end up with, okay, it equals this amount of neurons and this amount of layers, things like that. Worked really well. Very computationally intensive, of course, depending on the search space that you define. It has one flaw though, and that's why the other option that you have is a random search, because a grid layout might lead to missing out on optima, right? So if you have this grid layout of an unimportant parameter and an important parameter, which you don't know, of course, you might miss out on a potential optimum. So of course, by using a grid search, you have a limit to the number of combinations that is possible. A random layout picks random values for parameters and might, in theory at least, be better at identifying these optima. It works different because it never ends, so you need to set the distribution, also set a budget on how long do you want to look for it. And I personally don't have any preference for grid search versus random search. It's in the end all a question of computational resources. But these are just two different ways on how we can approach that. There's one word of caution though when we talk about optimization. So although grid search and also random search really help you in identifying good parameters, it is almost impossible to find the perfect parameters, right? So your performance metric usually favors certain types of combinations. Again, I talked about this precision recall trade-off. You have to limit yourself in the search space in advance, either when you're using grid search, the range that you're interested in, or random search, the budget that you set to it. So there is a limit to it. And so you will probably never find like the global optima from an operations research perspective, but still doing this is important. But when we talk about optimization, there's one caveat to it that we have to mention here. So typical errors, by the way, that happen in building your models are, on the one hand, the data leakage that I talked about, right? Well, there are multiple ones, right? Data leakage, having the wrong performance metric for the problem at hand. And now we come to the third one, which is overfitting. The issue with overfitting is that you need to find a good trade-off between the complexity of your model and not learning the data by heart. There's a very good figure in the introduction to statistical learning which explains really well what happens here. So let's start on the left. Let's say we know the actual distribution of the data. Let's say we even simulate that data, which is the black line that you can see over here. So we take this black line, and based on this black line, we now generate data points, right? So those points over here, those are our data set. And now what we can do is let's apply this to, let's apply an algorithm or multiple algorithms to this data set and see what they come up with. And that's what you can see over here. So we have three models, a yellow one, right? A linear one, as you can see, obviously. A green one, a nonlinear one, and a blue one, also nonlinear. And you can see the blue one is closest to our original distribution, which we know because we generated that data. And the yellow one simplifies why the green one is, as we say, overfitted. And it's important to look out for that. I mean, right here we know the real distribution, but we don't do that in the problems that we work with. So by comparing your performances in training versus testing, you can find out whether your model is either underfitting, right? So oversimplifying, or overfitting, which means learning the data by heart, right? So we have the different cases over here. You have the mean squared error for training and testing. So training is a gray curve. These are my results in training for my performance metric, MSE, and this one is the testing curve. And you can see for my perfect model, the blue one, which has a good balance between what we call, by the way, variance and bias. Those two results are very close to each other, and also they're the best, so that you can see that your model doesn't learn the data by heart. It works also very well on the unseen data from the testing set. This closeness can also be observed for the underfitted model, which simplifies, but it at least simplifies across the board. So that means that whatever results you get, they are comparable. Now it's interesting for this overfitted model, which is the most typical thing to happen. You would rather always overfit than underfit, especially with complex models. This is indicated by the flexibility scale here, by the way. And you can see this huge gap between training and testing. And if these scores vary that much, then you definitely have an issue with overfitting. If you use a cross-validation, this can be also observed. So in the cross-validation, if you can see a huge variance in the results of your central performance metric across these folds, then the probability is very high that your model is likely only learning the data by heart and therefore overfitting. So what you're aiming for is this blue model, this balance between variance and bias, not underfitting and not overfitting. And again, you have to check for that. For example, by plotting the scores in the cross-validation. So detecting overfitting is only possible by testing the model on really unseen data. And this has to be a subset of original data which the model has never seen, neither in the training nor in the validation phase. And that's why we have this idea of a global holdout set. And this global holdout set can never be used for any optimization purposes, right? Because this overfitting occurs naturally when you start to optimize. So that's why it's so important to have a global holdout set in this case, which was never used for any optimization, right? And then of course you have to leave it be. Don't then continue to optimize on your global holdout set. You have a separate test set or validation set for that. That's really, really important. However, again, as data is so sacred, there's also an option for cross-validation to do that. And that is called a nested cross-validation, right? This is an option that you can use to test the performance while optimizing the parameters. And it works by combining actually two layers of cross-validation, inner one and an outer one. So the inner one tries different combinations of parameters and then tests it on the outer ones. And this really helps you well in detecting overfitting, right? It will compare, you can compare the different optimal parameters in the inner cross-validation, right? You can look at the results of the outer cross-validation. So if you want to combine optimizing of parameters with a cross-validation, always use a nested cross-validation. Otherwise, you will overfit your model because it will optimize on these test sets which can never be used for it. And this is a very nice depiction on how that works, how you have these tuning of the parameters in the inner cross-validation, and that is then applied to a previously unseen one on the outer cross-validation, and this is repeated across the board, and by that you get pretty good results. Okay, nice. So let me shortly summarize what we learned today. First of all, there are multiple concepts for supervised machine learning, and the performance of each of the algorithms is determined by a lot of things, right? By the structure of the data, the capabilities of the algorithm, and how well it can capture the data. Things like the logic, is it a linear or non-linear relationship, things like that. Second, all of these algorithms can be optimized by tuning their parameters, which we just talked about. Third, it's really important to argue why you choose a certain performance metric and why it also suits your data distribution. And finally, that's what I keep stressing, right? But this interplay of your original problem statement, your data and data distribution, the algorithm that you pick and its capabilities and the performance metric, it all plays together and it all needs to serve a coherent story in the way that you choose and make these choices for algorithm for performance metrics, always with relation to your original problem statement. That's really, really important in my experience, is to look at this interplay that works well. Cool. Okay, so thank you very much, and see you for the next lecture.